Section 6.9, Electron Configurations and the Periodic Table. Our rather brief survey of electron configurations of the elements has taken us through the periodic table. We've seen that the electron configurations of the elements are related to their locations in the periodic table. The periodic table is structured so that the elements with the same pattern of outer shell or valence electron configurations are arranged in columns. For example, the electron configurations of the elements in groups 2A and 3A are given in Table 6.4. We see that all the 2A elements have NS2 outer configurations, while all the 3 elements have NS2 NP1 configurations. Earlier in Table 6.2, we saw that the total number of orbitals in each shell is equal to n squared, 1, 4, 9, or 16. Because each orbital can hold 2 electrons, each shell can accommodate 2 n squared electrons, 2, 8, 18, or 32. The structure of the periodic table reflects this orbital structure. The first row has 2 elements. The second, third row have 8 elements. The fourth and fifth row have 18 elements. The sixth row has 32 elements, including the lanthanide metals. Some of the numbers repeat because we reach the end of a row of the periodic table before a shell completely fills. For example, the third row has 8 elements, which corresponds to the filling of the 3s and 3p orbitals. The remaining orbitals of the third shell, the 3d, do not begin to fill until the fourth row of the periodic table and after 4s orbital is full. Likewise, the 4d do not begin to fill until the fifth row of the table, and the 4f orbitals don't begin filling into the sixth row. All of these observations are evident if the structure of the periodic table. For this reason, we'll emphasize that the periodic table is your best guide to order which orbitals are filled. You can easily write the electron configuration of an element based on its location in the periodic table. The pattern is summarized in Figure 630. Figure 630, Regions of the Periodic Table. This block diagram of the periodic table shows the order in which the electrons are added to orbitals as we move from the table from beginning to end. Notice that the elements can be grouped by the type of orbital in which the electrons are placed. On the left are 2 columns of elements depicted in blue. These elements, known as the alkaline metals, Group 1A, and the alkaline earth metals, Group 2A, are those in which the valence s orbitals are being filled. On the right is a pink block of 6 columns. These are the elements in which the valence p orbitals are being filled. The s block and the p block of the periodic table together are the representative elements, which are sometimes called the main group elements. In the middle of Figure 630 is a gold block of 10 columns containing the transition metals. These are the elements in which the valence d orbitals are being filled. Below the main portion of the table are 2 rows containing 14 columns. These elements are often referred to as f block metals because they are the ones in which the valence f orbitals are being filled. Recall that the numbers 2, 6, 10, and 14 are precisely the number of electrons that can fill the s, p, d, and f subshells, respectively. Recall also that the 1s subshell and the first s is the first s subshell, the 2p is the first p subshell, and the 3d is the first d subshell, and the 4f is the first f subshell. Figure 631 gives the valence ground state electron configurations for all the elements. You can use this figure to check your answers as you practice writing electron configurations. We have written these configurations with orbitals listed in order of increasing principal quantum numbers. As we saw in sample exercise 6.9, the orbitals can also be listed in order of filling, as they would be read off the periodic table. The electron configurations in Figure 631 allow us to re-examine the concept of valence electrons. Notice, for example, that as we proceed from chlorine, which is neon plus 3s2, 3p5, to bromine, argon 3d10, 4s2, 4p5, we have added a complete subshell of 3d electrons to the outer shell electrons beyond the noble gas core of argon. Although the 3d electrons are outer shell electrons, they are not involved in chemical bonding and therefore not considered valence electron. Thus, we consider only the 4s and 4p electrons of bromine to be valence electrons. Similarly, if we compare the electron configuration of silver and gold, gold has a complete full 4f14 subshell beyond its noble gas core, but those 4f electrons are not involved in bonding. In general, for representative elements, we do not consider completely full d or f subshells to be among the valence electrons, and for transition elements, we likewise don't consider a completely full f subshell to be among the valence electrons. Anomalous electron configurations. If you inspect figure 631 closely, you'll see that the electron configurations of certain elements appear to violate the rules we've just discussed. For example, the electron configuration of chromium is argon 3d5 4s1 rather than 3d4 4s2 configuration we might have expected. Similarly, the configuration of copper is argon 3d10 4s1 instead of 3d9 4s2. This anomalous behavior is largely a consequence of the closeness of the 3d and 4s orbital energies. It frequently occurs that when there's enough electrons to lead to precisely half-filled sets of degenerate orbitals, as chromium, or to completely fill a d subshell, as in copper, there are a few similar cases among the heavier transition metals, those whose partially filled 4d or 5d orbitals, and among the F-block metals. Although these minor departures from the expected are interesting, they're not of great chemical significance.